Well, hello students. This is Mr. Lin, and we're going to go over Atomic Structures 2. Below you can see a list of the topics that will be covered in this tutorial. Atomic structures is roughly about you guessed it, the structure of atoms. And over here you could see that the way that an atom is usually structured is that you have these positive bits in the middle called protons, along with neutral bits, and these together make up what's called the nucleus. And then around the outside you have these rings and shells of electrons. In the case of sodium, if you take a look on the periodic table, you can see that sodium is located right here. It is element number 11, which means that the atomic number for sodium is 11. The atomic number represents the number of protons that an atom has. This means that sodium has 11 protons, which I indicated over here. Now, this isn't always going to be the case, but when an atom is neutral, it should have the same number of electrons as well. And so if the sodium has 11 protons, it's going to have 11 electrons as well for it to be neutral. And we'll learn in a little bit that it doesn't stay that way for long, but let's come back to that later. The first thing you'll notice is that sodium has these rings of electrons around it. These rings can be figured, you can figure out how many rings an atom should have based on its position on the periodic table. Notice that sodium is located on the third row. This means that it's got 3 rings. If it was lithium, how many rings should it be around it? 2. If it's cesium, over here down on the bottom, you see that it should have 6 rings, and so on and so forth. These rings also have limited number of spots for electrons. They cannot cram them in there non-stop. And so that first ring, for example, is going to have room for only 2 electrons. The way that I know that is because in that first row, notice that it's got only space for 1 and 2 spots. That tells you that it's got 2 spaces for electrons. If you look at the second row, notice it's got 1, 2, 3, 4, 5, 6, 7, and 8 spots, which means that there should be 8 spots over here. 3, 4, 5, 6, 7, and 8. Okay, and the third ring, since remember sodium's got 3 rings, it's going to have the same as well. 1, 2, 3, 4, 5, 6, 7, and 8 spots for electrons. So I'll plug that in now as well. 1, 3, 4, 5, 6, 7, and 8. Now these are not like physical, something physical existing in these rings. These are just basically empty slots for electrons to be able to sit in. In sodium's case, remember it's got 11 electrons. Now electrons always fill from the inside outward. You never start on the outer rings. You start from the inner rings. And so the first electron is going to exist over here and over here. That's 2. The third electron would not be able to occupy the first ring anymore because there's no more space. So the third electron will jump to the second ring, as well as the next 7. We're now at 2 on the first ring and 8 on the second ring. That's 10. For the 11th one, just like that, we have to jump up to the third ring because there's no more space left for that 11th electron. That's how you plug in for sodium. If we take a look at another example, here we have chlorine, which if we take a look on the periodic table, you notice that it's got 17 protons, which must mean that it's also got 17 electrons if it's neutral. In chlorine's case, the first 2 electrons are going to occupy that first row. The second ring is going to give you another 8, 2, 3, 4, 5, 6, 7, and 8. The third ring is going to have how many valence electrons? Well, let's take a look at periodic table again. We got chlorine, which is all the way over here. If we count over from the left side, you notice that it goes 1, 2, 3, 4, 5, 6, 7 electron on that third ring. So let's give it a go. 1, 2, 3, 4, 5, 6, 7. And the last spot is empty. That's the one that basically would take it all the way up to this position. Notice that it's missing 1 electron to get there, and it's an empty space over there. Okay. Now, atoms like to have what's called filled octets, which just basically means that they want to have 8 electrons if they can. In sodium's case, it's got 2 options for how to do this. It can either gain 7 more electrons to be completely filled, or it could lose that 1 electron in order to get rid of that 3rd ring and be left with only the 2nd ring, which is already pre-filled with 8 electrons. It's much easier for it to lose that 1 electron over there. And if it loses that 1 electron, instead of having 11 electrons, it goes down to 10 electrons. That means that this is no longer a neutral atom, but what we call an ion. And this is the case because you have 11 positives, protons, and 10 negative electrons. That adds up to be a positive 1. Sodium tends to form positive 1 ions. In chlorine's case, this is reversed. Notice that it's got 7 electrons on the outside, so it can either lose those 7 electrons to get rid of that 3rd ring, or it can gain 1 electron in that empty spot. Much easier to gain just 1 rather than to lose 7. And so if it were to gain 1 more electron, remember it's gaining a negative electron, it's going to become 18 electrons instead. This turns it into an ion, specifically a negative 1 ion. Let's talk about what valence and core electrons are. So in the case of valence electrons for sodium, valence electrons are basically the electrons that you have in the outer ring. In sodium's case, it's only got 1 valence electron. For chlorine, it's got 7. The way you can tell that from the periodic table is based on its position on the periodic table from the left. So counting from the left, sodium has got only 1 valence electron in its 3rd ring, whereas chlorine, which is located all the way on the right side, has 1, 2, 3, 4, 5, 6, 7 valence electrons. Next, I wanted to talk to you guys about ionic bonding. Now, if sodium tends to form a positive 1 and chlorine tends to form a negative 1 ion, this is what they tend to look like. And if you have a single sodium and a single chlorine, they're going to add up to be 0 because you have a +1 and a -1. This is good because it satisfies, again, both of them gets to satisfy the octet rule. What happens is essentially is you have a single electron over here that sodium doesn't want, wants to get rid of it. And chlorine over here is missing an electron that it desperately wants. And so what ends up happening is we have this situation happen where that electron from sodium gets donated over to chlorine. And in this case, both sides have filled octets by turning themselves into positive and negative ions. Okay? The fact that they're matched up to each other in a 1-to-1 ratio means that the formula for sodium chloride is going to be sodium chloride, 1-to-1 ratio as well. Let's try another example. If we're dealing with magnesium chloride, the situation changes a little bit. Chlorine, just like before, it's going to form -1 ions. Magnesium, on the other hand, it's going to form something a little different. Let's take a look at magnesium. Notice that magnesium is also in the 3rd row, which means it's got 3 rings. And how many valence electrons does it have? That's right, it's 2. So 1, 2. Any atom that's on the left side of the periodic table tends to form positive ions. And in the case of the 1st row, these guys are all going to form +1 because they all have 1 valence electron that they're trying to get rid of. In the case of everything in the 2nd row, including beryllium, magnesium, and calcium, they're going to form +2 because they have 2 electrons to get rid of. Aluminum and boron and gallium are going to form +3. Now this flips when you go to the other side of the periodic table. When you have these guys over here, the halogens, they have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7, which means they just need 1 more electron in order to be a full octet. That means they tend to, instead of wanting to lose, they want to gain electrons, which will make them negative, and -1 because they're only 1 away from being filled octets. And so following the pattern, oxygen, sulfur, and all these rest is going to form a -2. Nitrogen, phosphorus are going to form -3. Carbon and silicon, these guys down the middle, do not tend to form ions because 4 electrons is just too many for the atom to be able to gain or lose. And so they tend to form stable octets by forming covalent bonds instead. So they do not form ions. And we're nearly done. So with magnesium over here, we note that it's a +2. And notice that right now, as it is, magnesium and chlorine, if they were in a 1-to-1 ratio, they would not add up to 0. This does not work. And so what we would need to do is we would need how many chlorines to match up to that +2? That's right, we need 2 of them. So if we had just 2 chlorines for every 1 magnesium, notice that this would turn into a -2. And this would then allow it to add up to 0. What this basically means is that for magnesium and chlorine to form an ionic compound, you're going to need twice as many chlorines as you do magnesium, which means the formula would be NgCl2. Okay. Last concept we need to talk about is something called ionization energy. When atoms want to gain or lose electrons, the difficulty by which they have to do it is something called ionization energy. It basically measures how hard is it to remove an electron from an atom. Now, if we take a look over here at this atom, we have 3 valence electrons on the outside and 2 core electrons on the inside. It wants to get rid of these 3 on the outside. And the way that it would do that is by basically getting rid of these guys one at a time. And so what we mean by first ionization energy is how hard is it to remove that first electron? Turns out it wouldn't be that hard because this atom actually wants to get rid of it if it can. In this case over here, this atom is in the second ring and has 3 valence electrons. That would make it boron, which is in the second row and has 3 valence electrons. It actually wants to get rid of those. And so that first electron, to get rid of it, it's not going to cost very much. And so because it will not cost that much, we see over here ionization energy for the first electron is going to be really low. The second ionization energy would be to remove this electron over here, which would not be that challenging either because it does not want that. It wants to get rid of all 3. And so if it gets rid of that second one, it's going to cost a little bit more energy, but not very much either. And the same thing goes for the third electron. Okay. Now we get to the place where all 3 of the outer valence electrons are gone. If we want to remove a 4th electron, you're talking about these core electrons, which it desperately does not want to lose. And if it does not want to lose it, it's going to be really, 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 really hard to remove it, which means a very high ionization energy. On the content assessment, you may be asked to identify which element belongs to these profiles for ionization energies. Notice that it basically would start off with like low ionization energies for every valence electron that's on the outside. So if you see 3 like low ionization energies followed by a 4th one that's really, really high, that should be a clue to you that this element, whatever it is, has 3 valence electrons on the outside because the 4th one is a core electron, which is really hard to remove. That's pretty much it. Good luck on taking the Atomic Structures 2 content assessment. Talk to your teacher if you need some more help. Thanks.